All right, we are going to take a look at problem G on the sample problem worksheet and see how to work that out. We talked about finding the standard cell potential, or E naught, if I have standard conditions of 298 Kelvin and 1 molar concentration solutions. But if I need to find the cell potential at non-standard conditions, then I'm going to be using the Nernst equation. So first off, let's start with, here's our equation. We're going to need to balance it, figure out what's being oxidized, what's reduced, what's the anode, the cathode, etc. So I'm going to start off with separating this out. So we see our 2 minus, and that is that, and the I minus, and that's that. Okay, so then we're going to go through the balancing process, and you already should know how to do this, so I'm just going to give you my final product here. So balance this, and 7 waters, and then we have 14 H pluses, and then that would be 6 electrons to balance charge. And balancing this thing, we've got a 2 over here, and 2 electrons over here. Before we can add together these equations to get our overall equation, remember that we need to make the number of electrons gained and lost the same before we combine equations. So this bottom equation, we're multiplying everything by 3 to give us 6 electrons. So my final overall equation ends up being 14 H plus, and that's aqueous. So it's pretty important at this point when you write your final equation to make sure that you know what the states of matter are, like is it solid, aqueous, gas, etc., because which things then make it into our Q. So again, to use the Nernst equation, we are going to need to plug in Q. I'll show you that in a second. And to use Q, we need to know which substances go into the equilibrium expression. And 3, I2. Make sure we're still in the shot. Okay, so there's our balanced equation for the reaction. There's a total of 6 electrons being exchanged. And, okay, so after we've done that, to use the Nernst equation, so this is the simplified down. This is at 298 Kelvin. So I'm using the very simplified with all of the constants already combined. This is that's the equation we're using. Okay. So first we need E naught. We need this number of electrons transferred, which actually we just found by looking at the half reaction, so that's going to be a 6, and then we need to find Q. So let's look at what Q would look like. So we've got some concentrations over here for the dichromate, hydrogen ion, iodide ion, and chromium-3 ion. So Q is going to be written according to this expression. So notice we're not including the liquid of the solid species, so it's going to be the concentration of Cr3 plus squared on the top, so making sure we use all the coefficients. We have concentration of H plus raised to the 14th, holy exponent, and then we've got dichromate, Cr2, that's a 2, O7, that has no coefficient, and then I, that's to the 6th. Okay, so plugging in, it'll be off the screen if I plug in, but I've got, so the chromium plus 3 on the top here, so that's 1 times 10 to the negative 5th, that's squared. Then I've got H plus is 1 molar to the 14th. I've got the dichromate is 2 molar, and then I've got the iodide is 1 molar, and of course that is going to be to the 6th, but that doesn't really matter. So plug all that in, and that gives you 5 times 10 to the negative 11th. And let's see if this will fit on the screen. 5 times 10 to the negative 11th. And so there you go. Okay, so that gives us Q. We have N to plug in, because that we said was 6, and so we need E naught, and then we're all set to go. So for these two half reactions, again, I'm looking for the dichromate. This is being reduced. So this is going to be at the cathode, so that's the first number that I'm going to pick out. So when I go to find E naught, I'm looking for the reduction potential for this, and that happens to be 1.33 from that reduction potential chart. and then I'm subtracting off the reduction potential for the oxidation reaction at the anode. And so again, the reduction potential for the reverse of this reaction, as written, is 0.54 volts. And so I subtract and give me 0.79 volts. So that's my E naught that's going to go in here. And so plugging everything in, so I have 0.79 minus 0.0592 divided by 6 times the log of 5 times 10 to the negative 11th. And you plug all that stuff in, and you end up with 0.89 volts. 0.89 volts. So notice with the concentrations that were given, we are not at standard conditions, and we've got a larger concentration of the dichromate ion, and we've got a very low concentration of the chromium-3 ion, which is our product. So we can see then that right now our potential is a lot greater than if we had those standard conditions, which is 1 molar. So again, when our Q value comes out to be such a small value, that means that equilibrium has not been reached. That means that we are to the right of, or sorry, that we are we're to the left of equilibrium, meaning we need to proceed to the right, the forward direction of the reaction, to produce more products to get to equilibrium. And so again, that's why we know that the forward reaction is spontaneous. We have a positive voltage for our cell, but also we see that it's a greater voltage than we would have at standard conditions. We've got a higher concentration for our reactant and a low concentration for the product. So there you go. That is solving for the non-standard conditions in a cell using the Nernst equation. Again, there's a whole bunch of different variations of basically this term, whether we've combined in the R and the T. So this is for 298 Kelvin. The Faraday has been wrapped into here, and also the R value in terms of joules has all been combined into this number. And again, you'll notice we've also got, this has been changed from natural log of Q, like we saw in the thermodynamics units, to just regular log base 10 for Q. But again, once you get all that taken care of, it's just plugging in the values that you need and getting your new voltage.